Okay, morning, everybody. Or actually, afternoon for you guys. So today we're going to finish off randomly connected networks and start talking about structure. Things have been a little bit abstract. So I want to bring us. So let's be really clear on what we're doing. So we're talking about a network of neurons. If we think of a single neuron, my pen has stopped working. Usually that means better. Hold on, let me change the battery. It usually fixes it. Uh-oh. Didn't work either. Bad situation. Oh, there we go. Okay. So, remember we have some neuron. Let's say that's neuron I. Do you guys have a question? Okay. Here's some neuron connected to lots of other neurons. Neuron 1, neuron 2, down to neuron K. And sort of the synaptic drive to this neuron. So this neuron has each of these neurons have some firing rate, new 1, new 2. So the drive to the neuron, synaptic drive, is equal to sum on K. So sum on J of Wij new J. Okay, so that's basically the drive to the neuron, but neuron's a nonlinear device. So the firing rate of our neuron I, new I, is some function. Well, the gain function, we usually put a new 0 in front of there to make sure it's firing rate of the sum on J of Wij new J. Okay, so that's the equilibrium firing rate. It's not a bad model. It's not exactly right, but it's pretty close. So the idea is if you know the firing rate of all the presynaptic neurons, if you know all the new J, all these, you're going to know the firing rate of this neuron. Now that's a static picture. But we can write now tau, some time variation, tau d nu I dt minus nu I. And this equation just says, look, if the firing rate of the neuron is too low, so So if this number is really big, so this is big, and that's small, in that case, the firing rate of our neuron goes up. D nu dt is positive. If it's the other way around, this is other way around, the firing rate goes down. So it's sort of a reasonable, approximate picture of what networks of neurons are doing. It's still a lot of equations, right? There's still a typical network of neuron. So each neuron connects to each neuron makes one. So each neuron makes about 1,000 connections. But they're about on the order of, they're 10 to the 6th to 10 to the 8th neurons in a network. So even though we reduced our sort of equations to some linear, some nonlinear differential equations, there are a lot of equations here, right? So this is now 1 million or 100 million or 10 million or 100 million equations we need to solve. Which is pretty hard, but we made a huge approximation. And the approximation that basically we made was that the approximation the one firing rates are sort of, we ignored temporal fluctuations. We basically ignored spikes. So ignoring spikes is basically what allowed us to write down this equation. But the other approximation we made was all weights were the same. So weights were, well, not all weights were the way. All weights of a particular type were the same. So that means Wij, let's say E to E, that's connection from excitatory neurons to excitatory neurons. We just replace it by a signal number. Okay. And that allowed us to write down, tau. The idea is tau D, let's say tau E, D nu IE dt equals nu 0 phi of, basically there were k number of connections per neurons, WEE nu E minus k WEI nu I minus nu IE. So k, remember, is always number of connections per neuron. Okay. And what that means is that nu IE is the same for every neuron. Right? So nu IE just equals nu E. So that gave us an equation for now, instead of neurons, it's for actually the whole population. So the idea is the whole population every neuron is doing the same thing, tau E d nu E dt equals nu 0 phi of k WEE nu E minus k WEI nu I minus nu E. And tau I d nu I dt equals nu 0 phi of k w I e nu e k w I nu I minus nu I. Okay, so these are actually known as the Wilson-Cowan equations. And the original paper, if you want it, is on the website. And they're surprisingly, even though it's a very, very simple model, the equations are surprisingly rich. Okay, let's copy this. Okay. And in fact, they gave us what we call the Wilson-Cowan null points. Okay. So if you plot nu e on this axis, so nu e on this axis, nu I on this axis, you got basically, this is a curve so this is the curve along which d nu e dt equals 0. So that equals 0. This is basically 0. That gives you a null line. And then we had another curve. This is d nu I dt equals 0. So if we said that's a 0, we also get another null line, inhibitory null line. Okay. And, I derive these. It's actually relatively simple to understand where they came from. So for instance, the excitatory null line, if you fixed, oops. All right. So if you fix the excitatory inhibitory firing rate to this value, okay, let's call this nu I0. We fix it to some value, then what happens? Our equation for the excitatory neurons becomes tau e d nu e dt equals nu 0, becomes a function of one variable, k w e nu e minus k w e I nu I0. So this is fixed minus nu e. Okay, and this, if nu I0 is large enough but not too large, this is going to have two solutions. Okay, if we plot it on this axis, this function here, for this whole function here, and plotted it on this axis, and we plotted that versus nu e, okay, because nu I0 is some positive value, this quantity here is so this term here, it starts off at 0. starts off at 0, and then it goes up, and then it saturates. So this is this function here, right? And the reason it's 0 down here, it's 0 down here because of the inhibitory fine rate. Okay, because nu I0 is non-zero, it starts off 0. It takes some excitatory drive to overcome that. And if we now plot sort of nu E, which is this term, it's this. So this point here corresponds to this point here. This point here corresponds to this point here. And this point here corresponds to this point. Okay. So we will label this as A, B, and C correspond to A, B, and C. Okay. And the fact this saturates, so real neurons really just can't fire above 100 hertz. Okay. Now, the linear integrating fire neuron we wrote down actually can fire at a much higher rate, but for realistic neurons, it goes over like that. And you can do the exact same analysis if you fix nu I0. Let's call this nu E0. And you wrote down an equation for the inhibitory neuron, which is tau I d nu I dt equals nu 0 by now KWEE nu E0 minus KWEI nu I0 is nu I minus nu I. Now we think of this function as a function of nu I, and now there's only one solution, okay? Because the right-hand side is a decreasing, the whole right-hand side, this whole term here, is a decreasing function. So this is this whole thing is a decreasing function of nu I. So basically, it just goes down. There's only one solution. Maybe it's even worth plotting this over here, sort of on a small scale. Plot it over here. If we take this whole term and put it on the x-axis, it's just basically it's just some decreasing function. And then when we plot the intersection, now there's only one intersection. We'll call that D, and that corresponds to this D over here. Okay? So those should be easy to understand. So this relationship between these gain functions, so these functions here, and the null clines. Okay? And this in some sense, and so the other thing is that if we look at, we can actually get a lot more information than just equilibrium. Okay? So we know that at fixed inhibitory firing rates, the nu EDT is positive here, right? Because this arrow here, I'll call this BC, corresponds to this region here, where the sort of gain function is larger. This is positive here, but the red is larger than Over here, you push in this direction. Okay, and then for the green curves, you actually just push down. Inhibitions cause you to stabilize, and that makes this term, this point here, it causes, what that means is neurons tend to, if you start here, you tend to oscillate a bit. Okay, and if you look in the brain, if you look at reports of neurons, the networks of neurons do tend to oscillate. So it's very consistent with this picture. Okay, so this is a picture we have. This is a summary of what we've done. We made this really large approximation here. This really big approximation here where all weights of the same type were the same, okay? Which, of course, they aren't in the brain. Nothing's ever the same in biology. What we want to do now is drop that assumption. We want to basically explain two things. So we want to explain two observations that we see in the brain all the time. One is when there's neurons have a range of firing rates. And two, spike times are irregular. Okay, so remember back to our old picture, this whole model was based on model for membrane potential. Which was tau dvi dt. V is now voltage. So this is now voltage. Voltage on neuron I. E equals minus a linear integrate fire, Vi minus E leak, plus the sum on J, current-based model, Wij Gj of T, or E minus Wij Gji of T. So far, replace these by firing rates. The new IE and new I. So if we do that, the memory potential is going to look, as we saw earlier, this is resonant threshold. It's just going to basically, it's going to go up, fire spike, come back down, go up, fire spike, come back down. So spikes will be very regular. Okay. So what we want to do is understand two things. We want to understand, first of all, why neurons have a range of firing rates, and second of all, how you get irregular spikes. So we'll do that now, and then we'll start talking about structured networks. Okay, so the first one is actually sort of, it's pretty straightforward how to get so we'll copy this over. So it's pretty straightforward to get a range of firing rates. So all we have to do, so in the old days, we let basically Wij, and I did this last time, go to W, which is a constant, plus delta Wij. So of course these have superscripts E and I, but we could drop those for a second. This is constant. And these are random fluctuations. Okay. And what we're going to do, we're going to still assume, we're going to still let a sort of a time varying conductance is equal to firing rate, nu J. But now we're going to see what happens. So with sum on J of Wij's, nu J equals the sum on J of W plus delta Wij, nu J, and that equals W, the sum on J of nu J, plus the sum on J of delta W, I, J, nu J. And this, of course, gives us old friend. This is K, number of connections per neuron, W times nu, call it nu bar. This is the average firing rate. This is 1 over K, sum on J, nu J. Okay. So for simplicity, we'll sort of assume that there are, let's make things really simple and assume that there are only K neurons in our network. Only K, they're basically we'll assume there are K excitatory and K inhibitory neurons in our network. It's really only K connections per neuron, but if we assume they're exactly K, it's a little easier. Otherwise, we have to worry about all sorts of other randomness. But so it's really easy. This K number of connections, neurons, the weight times the average. So what about this term? This term here. So what I'm about to tell you is sort of the most important thing I can tell you in this class. So definitely, so it's also pretty non-trivial in a way. I mean, in some ways it's easy, in some ways it's not. So we're adding up, K random variables. And so, these things are, sometimes delta Wij is positive, sometimes it's negative. On average, it's 0. But what we want to know is its standard deviation. So on average, so it's 0 on average. So how big are fluctuations? What is the variability? Okay, so it's not going to be exactly 0, right? For some value of I, it's going to be large. For some value of I, it's going to be small. So let's compute the variance. So the variance with respect to index I, okay? So different values of I have different, the sum's going to be different. So that's basically, this is equal to 1 over n, 1 over k, the sum on I. This is a calculation I did yesterday, but it's worth doing twice. Sum on j of delta W ij nu j squared, which is equal to, put in all the steps, sum 1 over k, sum on I. The square is just a sum on j of wij nu j times the sum on j prime of wij prime nu j prime. Okay, we haven't done anything. We just rewritten the square. But now we have a sum on I, j, and j time. We're going to rearrange things. Sum on j and j prime of nu j prime times 1 over k, the sum on I of delta wij, delta wij. Okay. Now, if j is not, these are a bunch of independent random variables, and that's about 0. So this quantity here is equal to the variance of w if j equals j prime, and 0 if j is not equal to j. So that just gives us, when j is not equal to j prime, there's no sum. So this is a sum on j of nu j squared times the variance of w. Okay. And that is equal to, we can, this is equal to 1 over k here, 1 over k here, actually 1 over k here, and a k here. And this quantity here is just nu squared bar. Okay. So what this means is the variance of this quantity with respect to index I. So it's gotten a little messy. So there's a factor of k, a factor of nu squared bar, and then the variance of w. Okay. So we have the sum on j of wij nu j is equal to k w nu bar plus some term, I'll call it, I don't know, give it a name, zi. So the variance of zi is equal to k, the average of nu squared times the variance of w. Okay, so we're going to write this, we're going to write zi, the square root of k nu squared bar, variance of w, times squiggle I, where this is a zero mean unit variance it's actually a Gaussian random variable. That doesn't really matter so much. Gaussian random variable. So that's actually kind of convenient for some calculations, but we don't really care. So we're going to write this as a sum on j of wij nu j equals k w nu bar plus the square roots of K nu squared bar variance of W times squiggle I. Okay. So this is extremely important. It's going to come up again when we talk about structured networks. And it sort of makes sense, right? If you have a bunch of zero mean random variables, it's going to be smaller. So this term here, so when these things are non-zero mean, we get a factor of K. Okay. When we average non-zero things, we get a factor of square root of K. So square root of K here versus K. So it's a big, big difference. So K isn't huge, it's around 1,000, but that gives us a factor of 30 difference. So what that means is the firing rate of, so now we can actually, now each neuron is different. So tau, I'll write actually tau d nu ei, firing rate of neuron I. It's still the same gain function, right? Nu of phi of, so what really went here was a sum on J of Wij EE nu JE minus the sum on J of Wij EI nu JI, okay, minus nu IE. So now we can replace these by the preceding formula, and that gives us nu 0 by, there's a K WEE nu E. And then plus the square root of, we have a K nu E squared bar. So that's the average of the square of the excitatory firing rate, variance of WE times squiggle EI minus K W EI nu I bar, thing we've seen before, and again plus the square root. We have a K nu I squared bar variance WEI times squiggle I, and then minus nu IE. So when you have two Gaussian random variables, it's kind of nice. You could add them together, and we can write this as nu 0 phi of K WEE E minus K WEI nu I, and then plus the square root of these things just add together. We have K nu E squared bar variance WEE plus nu I squared bar variance of WEI times squiggle I. Okay. Minus nu. Okay. So basically, we've taken our standard old gain function, which we've seen before, and each neuron has sort of a different value. So squiggle I is this zero mean Gaussian random variable. Goes basically between plus or minus 1 more or less. And so each neuron has a slightly different synaptic drive. And what we want to do now is test, okay, given the size of this thing, so how big is this thing? So this thing is about, the size of this thing is square root of K, very loosely, times nu, the square root of the square, because, and then times the size of W. Okay, very loosely. So this is some, we're actually taking the square root of average variability squared. It's got, scale five rate. Maybe it's a little bigger than the firing rate, maybe it's a little bigger than W. But that's a scale. And given the scale, we can ask, does that count for the spread in firing rates? Okay. So the equilibrium of our neuron, equilibrium firing rates is sort of let's switch back to black. So nu IE equals nu zero pi of KWE nu E minus KWEI nu I plus, I'm just going to put some number here. So root K, this is sort of a nu W. So nu W is shorthand for this term here. It's shorthand for all this. Okay. Times squiggle I, a random variable. And we can ask, given this, does that account for the spread in firing rates? So the spread in firing rates is, typical firing rates is 2 to 5 hertz, and the spread is 10 to 15 hertz. It's a big range of firing rates. And does this account for it? So remember what our gain function was. Our gain function from a long time ago was nu zero divided by minus log of 1 minus delta V is the distance from rest to threshold over, now it goes in here, K W E E nu E minus K W E I nu I plus root K V W squiggle I, or nu W squiggle I. This is a firing rate. Okay, so this is a kind of complicated nonlinear expression, but we use the fact that for small epsilon, log minus log of 1 minus epsilon, it's approximately equal to epsilon. So we get nu IE, and the firing rates get big, is equal to nu naught. Now we divide by this thing, so we have K KWEE nu E minus KWEI over delta V. And then we have plus this term, root K, nu firing rate, typical weight, squiggle I over delta V. So delta V, remember, is around 50 millivolts. Okay. So the fluctuations, so this is going to be sort of, in some sense, this term here is going to be our mean firing rate. So this is our mean, and these are going to give rise to fluctuations. Neuron to neuron variability in flux. Can't spell. Fluctuations. Okay, and we can ask how big are those fluctuations. So we could sort of say, delta nu I equals nu zero square root of K W over delta V. Remember, W, is equal to V PSP approximately times tau. Okay, and nu zero, if you remember, is equal to 1 over tau. And and then we left out a factor of u. So this is something like the square root of k, and k, remember, is around 1,000. So the tau's cancel, and we just get about square root of k is around 30 over 15 times nu. 2 times nu. Okay. So this seems a little bit small, but it's in the right ballpark. Remember, if you go back here, we just call this nu w. This is going to be nu squared. The square root of nu squared bar is going to be bigger than nu. We have factors of 2 to 4. We have other factors going around. So this is more like between 2 and it's more like from 2 to maybe 5, possibly. Okay. And then if so the firing rate is 3 or 4 hertz, so this thing is easily 10 to 20 hertz. Okay. So the fluctuations in firing rate are very consistent with what's observed. So it's kind of nice. So we start with a simple linear integrating firing model. We did some back of the envelope calculations. We know there are fluctuations in synaptic strengths, and it gave us about the right fluctuations so that's good. So we haven't, basically it's a little bit of a sanity check. We haven't screwed up. We want to look at one more thing, and that's fluctuations in firing rate, which is a little bit harder, but it's the same idea. So if you go back here, what we really have, if you look over here, we have some time-dependent synaptic drive associated with spikes. So just to remind you what GJ is, so GJ of t versus time. So this is basically spike times on neuron J. J. And every time there's a spike, this jumps up. I mean, use a normalization, so the area equals 1. Okay, and sort of a reasonable approximation for this is e to the minus t over tau s, so that divided by tau s, and then theta of t, where tau s is around 5 milliseconds. Okay, so that's our picture. And given that, we wanted the sum on J of Wij dj. And we can write that as a sum on J of Wij nu J plus the sum on J of Wij Gj minus dj. We're going to call this delta Gj. Okay. And so this is a time varying quantity, right? Especially because we're summing on J. If we plotted this quantity here versus time. So this is, let's say this is 0. It's going to be some fluctuations. Okay. And what we want to know is the amplitude of these fluctuations. How big are these fluctuations? So these are now temporal fluctuations. And we're going to do the same thing. So this is, we're going to write this quantity here as a sum on J. Again, we'll let W equals W plus delta W ij delta gj of t equals w, the sum on j, sorry, w, sum on j of delta gj of t. And this quantity here is actually, we're going to ignore, plus the sum on j of delta w ij delta gj of t. Okay. So this quantity here is actually, so these are coherent fluctuations, meaning all neurons are doing the same thing. For complicated reasons, those are small. And they're basically small if you go back to our nucleons. They're small basically because we're very strongly attracted to this point. And that tends to kill those. It's actually a really complicated story. But we're going to focus now. So we'll focus now on this term. Oops. Focus on this term here. And again, we're going to square it, an average. Actually, we're just going to square it. So we're going to square square it, take this term, square it, and that's the sum on j of delta w ij. Delta gj, and then sum on j prime, delta w I prime, delta d prime, equals the sum as before on j prime, delta w prime, delta d prime, which again is approximately equal to, this is so 0 if j is not equal to j prime. So again, it's a variance of w times delta gj squared of t. You kind of want to average this over. Okay. And again, we get sort of root k scaling. And again, because of the root k scaling, times the variance of times the square root of the variance of the weights, times the square root of the variance of the weights, and then times this term, it's about the same order, right? So it's k, sort of this k square root term here, is the term we saw here, and that gives about sort of this factor of 2. So basically, variability in the weight. So it's a combination of two things: variability in the weights, and the fact that the weights are about the right size. Okay. Gave rise to fluctuation, variability in firing rates. Give rise to variability in firing rates that we saw here. This sort of 10 to 20 hertz variability in firing rates and temporal fluctuations. So it's sort of the variability in synaptic strengths is responsible for both things: temporal fluctuations and variability in firing rates. Okay. So to summarize, we started with a really simple model of, it was sort of this. This is our starting model. Okay, just a simple model for the membrane potential voltage. We turned it into a firing rate model, and we got out the sort of this picture, a kind of a non-trivial picture of dynamics of excitatory and inhibitory neurons. So in phase plane, they look like this. We have the famous Wilson and Cowan nucleons. There's a lot of evidence that this is where the brain operates. You see oscillations, which is predicted by right? Spiraling around here. You see relatively low fine rates. They're quite stable. You see a few other phenomena which I won't talk about. But this is a very, very good model of bulk properties of neurons. Okay. What it can't explain, of course, is how neurons compute complicated things, and that's what we're going to talk about next. We're going to add structure. We started with random connectivity, and we can now add structure to that and see what that does. Okay, so let's take a 5-minute break, and then in 5 minutes, I'll come back and start talking about structured networks. Okay, so let's start up again. Before we talk about structured connectivity, let's sort of talk about why random connectivity doesn't do much. So let's go back to this equation here, which we had an equation for, t here. Okay. Let's go back to this equation. So we had two terms. We had our standard old term from our sort of non-random connectivity, and then we had a term from random connectivity. Okay. I'm going to actually write down this equation, but instead of doing inhibitory firing rate, I'm going to do instead of writing an equation for excitatory firing rate, I'm going to write an equation for inhibitory firing rate. And I'm going to write it sort of in very much shorthand. So I'm going to write tau I d nu I dt is equal to nu 0 by k w e actually w I e nu e. I'm going to actually fix the excitatory firing rate to some value and just focus on inhibition, w I nu I, and then plus some term which I'll just give it a name, sigma squiggle I. Those are the fluctuations, minus nu I. This is actually for a single neuron, not for whole population. In fact, actually, let's assume that the excitatory firing rate all of the same firing rate and the same strength. So we'll actually just put here, so k nu I squared bar variance of w squiggle I minus nu I. Okay. And so this term here, these things here came from the sum on I, sum on J of W I J I nu J I. Okay. And for the sort of the mean parts, we got a term that was proportional to K. For the fluctuating part, so the term proportional to K, and then for the fluctuating part, we got a root K. So mean, I think that we can write remember Wij equals Wii plus delta Wi. And the main point is this term led to a factor of K. And this term led to a factor of square root of K. It's much smaller. Fluctuation didn't do anything. Okay. So random fluctuations are not especially useful. And so they don't really do much. We can relative to the K ones, they're small. So we want to add structured connectivity that has a much larger effect. So instead of adding random, so let's add structured connectivity let's add sort of some non-random piece. Okay. And so the reason things went, well, so let's just add it and we'll sort of see what happens. So so we're gonna let Wij I, actually the fact is I is not so important, equals Wii plus delta Wi. And then plus, I'm gonna give it I'm gonna give it A to I. Okay, so A to I is, so each of the A to I's, so A to I is A to I squared is about the same size as Wii. Okay, on average. So the size of this term says A to I, A to J. Okay, so A to I, A to J is on the same order. So these things, so all these terms are about the same size. All terms about the same size. But they have very different effects, okay? So this term here always sort of gives a factor of k. This term gives a factor of root k. Because it's random, right? Basically when you sum it, it gives a random term. So what about this term? So this term depends. So the sum on j of A to ij nu j is equal to A to I, the sum on, A to I, the sum on j of A to j nu ji. So let's say this is random. Okay. Now, whether or not the size of this so the size depends on nu ji. Okay. If nu ji is also if sort of nu ji is also lined up with A to J, let's go to the next slide. So if nu ji equals sort of nu I plus some number beta times A to J, in that case, the sum on J of A to J nu J I equals the sum on J of A to J nu I, which of this thing, because it's random, is small, plus the sum on J of A to J beta A to J. So this is sum equals 1 to K. Equals beta times K. Okay, so in that case, the sum on I of A to I, A to J, our structured connectivity nu J, is approximately equal to, beta times K times the average of beta squared, which is basically beta squared times the size of W. If you go back here, so it depends on basically what the firing rate is, which is exactly what you want in structured connectivity. You want structured connectivity to give you some dynamics that it's going to pick out some particular firing rates. So that was a really, really hand-waving kind of loose explanation of what you want in structured connectivity. And the key thing is, so this term here is very much random. This is highly non-random. You know, chances of if you show some connectivity random, you'll never get something. This is actually called a rank one matrix. So for structured connectivity, we're going to consider Hopfield connectivity, sort of following this line. And we're going to consider a model where Wij goes to what we call Jij. I'm going to use 1 over, I'm going to actually switch to n of the sum on mu. Now we'll multiply these things, eta I mu, eta j mu. So now n equals the number of neurons. And it's all-to-all connective, all-to-all connective. We're going to drop this in a little while. So every neuron is connected to every other. And we're going to also consider a very simple model, a really very, very simple model. This is the original Hopfield model. This is Hopfield 1981. So the paper's on our website. 1980. And so basically the activity of neuron is SI, it's discrete time, SI of t plus 1 equals the sine of the sum on j of Jij, Sj of t. Okay. So we can think of, you know, Sj is positive, it's emitting a spike, negative is not emitting a spike. The time between t and t plus 1 can maybe be 10 milliseconds, time constant. So it's a very, very abstracted model of a network. But it gives the right idea, and we'll see how to include this in an actual network of spiky neurons at the end. Okay, so we're going to analyze this model, and what are we going to analyze it for? So sine of sum on j of Jij is 1 over n. The sum on mu. Oops. Mu of eta I mu, eta j mu, Sj of t. I need to tell you what eta is. So eta I mu is completely random variable. It's plus 1 with probability 1/2, and it's minus 1 with probability 1/2. Okay. So this is going to be a model of memory. And the first thing you do whenever you get an equation is look for fixed points. So we look for fixed points. But first we want to interpret this and see what we're going to expect. Okay. So what's the interpretation of this? So in some sense, so let's consider the case mu equals 1, a really simple case. And so remember, so mu equals 1 to p. So p is the number of patterns. So we consider a really simple case of p equals 1, in which case jij equals 1 over n eta I is 1 eta j 1. Okay, and remember eta I1 is equal to plus 1 or minus 1. Plus 1 or minus 1. So we can take our group of neurons and we can divide it in half. So for this half of the neurons, so for this half, eta I equals plus 1. And for this half of the neurons, eta I equals minus 1. Okay? So two neurons in here, for these two neurons, the connection strength is, remember the connection strength is going to be, if both eta I, so this is I and this is j, so if eta I1 so eta I1 equals eta j1 equals 1. That means the connection strength is positive. So that means basically j is 1 over n, it's plot positive, right? So for any neuron in this group, the connection strength is positive. Okay? For any neuron in this group, the connection strength is also positive. Okay, these connections are all positive. Positive, positive, they're all recurrently connected. So they all excite each other in this group. Across from one to the other, though, the connection strength is negative, right? Because here, so on this side, eta I is minus, on this side, eta I is plus. So, you know, eta I from one side times eta I from the other side is going to be, so the connection strength here is going to be 1 over n plus 1 times minus 1 equals minus 1. So neurons from one side inhibit neurons from the other side. So it looks like there are two possible stable states. Okay, so one, call these plus neurons. These are plus neurons. And these are minus neurons. So minus neurons. So two stable states is, you know, all plus neurons have activity 1. S equals plus 1. And then all minus neurons have Si minus 1, or it could be Si equals minus 1 and Si equals plus 1. Okay? Because then, I mean, when we say inhibit the neurons, the connection strength is negative. So if we have, you know, Si p plus 1, well, actually, let's just do so we have the sum on j of eta I 1, eta j1, that's j. So if we can divide this in equals the sum over, you know, j plus eta I Si minus the sum over j minus of eta I. Right? Sum over j plus means all the sum over all the neurons in the plus group, all the neurons in the minus group. So now we can say Sj. So now these are all positive, all plus 1, all minus 1. Then if eta I is positive, we get a plus 1 half, eta I is negative. Okay. So the idea is basically you have excitatory connections in here, excitatory connections in here, inhibitory net connections across here, inhibitory connections. So we're not worrying about Dale's law. We're just trying to get this. So for a single neuron, for a single population, the fixed points involve something non-trivial, right? Half the neurons on and half the neurons off, the other way around. Let's now analyze the more interesting case of when we actually have p terms. So we're going to analyze this case. Equals 1 to p. So let's copy this over. Okay. So here's our equation. Sj of t plus 1 equals that. And so here's our guess. A stable state of this Sj equals eta I mu is a stable state. And actually, let's make it eta I mu. Okay? So mu equals 1 to p. So that means if that's true, that means there are p stable states to this network. Okay? And we'll see, and we can think of each of those stable states as a memory. Okay, so the network goes to some stable state, it's a memory. In terms of dynamics in S space, the idea is that, so if this is S space, these fixed points would, under dynamics, would go here. And that would allow you to memorize things. It's actually called a content addressable memory, because you can start here, remember something partially, and then recall it. Go back to that a little bit. Okay. So in the last few minutes, it's actually quite easy to show that this is a case. So basically, it's a stable. This is our guess. So if that's correct, we'll have eta. This should be S. We'll have eta I mu equals, and we'll put a question mark because we don't know if this is true yet. The sign of the sum on J we'll put a 1 over n here. So the sum on mu equals 1 to p of eta I mu eta j mu eta j mu. Okay. We'll rearrange terms a little bit. Sine sum mu equals 1 to p eta I mu, and then 1 over n, the sum j equals 1 to p sorry, j equals 1 to n. There are n neurons in the network of eta j mu eta j. Okay, and we're going to break this sum here into two terms. Okay, there's a mu equals nu term. So if mu equals nu, then we get 1 over n, the sum on j equals 1 to n of eta j nu squared equals 1. If mu not equal to nu, we have 1 over n sum j equals 1 to n of eta j mu eta j nu. So this, of course, now this is zero mean random variable, right? So this is basically half the time it's plus 1, half the time it's minus 1. This actually goes to 1 over root n. We'll be a little more clear about that in a second. But the idea of breaking this thing up into u equal to 1 and mu not equal to 1, mu equal to nu and mu not equal to nu seems like a good idea. So we're going to write this as sine. So we already saw when mu equals nu, we get a 1 out. So we get eta I nu plus 1 over n, the sum mu equals 1 to p, the sum j equals 1 to n of eta I mu eta j mu eta j. Okay, so the question is, how big is this term? I'll copy it to the next page. Equals so in this sum, we have mu not equal to nu. Okay. So in the sum, mu not equal. So basically, there are n times p minus 1 terms in the sum. And they're all uncorrelated. Okay, and that's because eta j nu is independent of everything. Okay, number eta j nu is completely random variable. No matter what you pick for j or nu or mu, it's uncorrelated. And so basically, we have the sum. We can think of this as the sum from some other index k equals 1 to n times p minus 1 of zi. And zi equals plus 1 with probability at half, minus 1 with probability at half. So it's 0 on average. And how big is it? So we want to know its standard deviation. So we're going to square it and add it, okay? So we're going to square this thing. So 0 on average. So we're going to square it. So variance equals, we're going to square it, sum. And the reason it's either plus or minus 1 is because eta, all the etas are plus or minus 1. So these are all plus or minus 1, products of plus or minus 1. So we have sum on k of zi, sorry, zk squared equals a sum on k, and we're going to average this. Sum on k and k prime, the zk prime This is basically the calculation we've done before. Sum on k and k prime, zk prime. So this equals 1 if k equals k prime, and 0 if k is not equal to k prime. And we just get the sum k equals 1 to n p minus 1 of 1, zk squared, and zk squared equals. So this equals n p minus 1. So the typical size of this, the sum on k equals 1 to n p minus 1 of zk, goes as the square root of n p minus 1, and again times some random variable, squiggle. So we have about 1 minute. So I'm just going to write down what this is. So this quantity here, this whole quantity here, because we've divided by 1 over n, is basically the square root of n p minus 1 over n equals the square root of p minus 1 over n. Okay, so we go to that page, back to this page, this quantity here is the square root of p minus 1 over n. And this thing here is plus or minus 1. So as long as it's times some random number, squiggle, I'll squiggle. The squiggle I is zero mean, unit variance. So as long as p is not so good, this really is a fixed point. And we're going to actually, I'll go into that in more detail next time on Monday, and then we'll talk about other kinds of structure. And after that, I think we're going to switch on to learning. Okay, so as usual, it's going to be on the website. I managed to record it this time. So I'll see you guys next week, next Monday.